We're now going to speak about NumPy, but first I'll begin with a quick introduction to that, with something I decided quite dramatically to call the dark secret of Python. So I didn't hide it from you that I really like Python, and on every opportunity I had, I praised and glorified Python and said how awesome this language is, and it really is. But it's important to recognize that Python also has some important limitations and drawbacks. And I think the one most notable to recognize about Python is the efficiency of the language. So Python is not efficient, especially compared to languages that do put emphasis on efficiency, like C and Java. And that's especially the case when we speak about CPU-intensive tasks. So when we speak about tasks where most of the time goes to the actual processing of the data using your CPU, as opposed to, for example, I don't know, storage-intensive tasks, or where most of the time goes to just reading things from your hard disk or taking things from the internet or memory-intensive. So if we speak about something which is CPU-intensive, so we're doing some calculations, say some mathematical calculations, then Python could be very, very inefficient. And that's even not too rare to see cases of even 100 times slower, which is really staggering. And we'll actually see examples of that, where Python is really, really slower than other languages. And if we want to understand why it happens, I think there are two main reasons why Python is inefficient. One has to do with a thing called the garbage collector, which is something that happens at the background of Python when it tries to manage the memory in such a way that will be convenient to the programmer, for example, as opposed to languages like C, where you have to do more manual management of memory. But I think actually the main reason that it happens is because Python is what is called a dynamic language, which is something I mentioned in the past but didn't quite explain what it means. So let's, for 1 minute, have a closer look about what it means, a dynamic language, and why it's very nice as a programmer to work with a dynamic language, but why it might also create problems for efficiency for the computer that actually has to run the software. So as a very simple toy example, let's look at a source code of just writing x equals a plus 3. Okay, we just want to execute this line of code, which is a very simple one. Now, in static languages, we need to pre-specify the type of every variable. So if we write this code, for example, in C, we would have to decide at the beginning of the program that x is an integer and a is also an integer. And that would be the case along the entire flow of the program. Okay? And so when this code is compiled into binary code in static languages, then it's very straightforward to compile it. It just turns into one atomic operation of the CPU. So we speak about the actual CPU processor in your computer, that it executes some calculations. And it supports all kinds of atomic operations. And one of them is an addition, where it can take just one value from one memory address, add to it some value, and store it in another memory address. So in a static language, it would look something like this. You would go to the memory address of the variable a. You would add 3 to that and store it in the memory address of x. And that's actually just one CPU operation. So there are actual physical transistors in your processor which can do exactly that operation. And there is nothing more about it. Now, in a dynamic language, on the other hand, what happens is we cannot know in advance the type of A, and what even we mean by plus. So all of that has to be determined in real time. And even if you execute this code 1,000,000 times, say, within a loop with 1,000,000 iterations, on each single iteration of the loop, this will have to be decided from scratch again, because in theory, you could change it along your flow of the software. So if we were to execute this line of code in a dynamic language, what your computer would have to do is something along these lines. It would first need to read this command from your memory. Then it would have to search for a variable named a. Because again, in dynamic languages, you don't pre-specify all the variables. Instead, Python keeps something like an internal dictionary with all the variables and mapping like each variable name to its content. So it would have to look for a variable named A. Then it would have to determine the type of A, saying, for example, that it's an integer. Then it would have to validate that this type indeed supports the plus operator. So the plus could mean many different things in Python. It could be a plus for integers. It could be a plus for strings. These are two separate things. So it now says that it's a plus for an integer. And then it would have to call this operator with the value 3. So again, it would have to determine the type of 3. And only then call the respective native code. So only in this step, the CPU actually performs the operation that you intended to perform. And then it would have to store the result along with its type, the variable name, and everything, and set all the values. So I think you can easily see how this very easily translates into like 100 different atomic operations on your processor if you do it like that. And that's actually the cost that you pay when you work with a dynamic language, which is very nice to use, but far less efficient for the CPU. OK, is that clear? OK, so that's what happens. But there is a bright side to it, which is something which is often called the 80-20 rule, which was invented by this nice Italian guy called Vilfredo Pareto. This was originally, I think, was originally applied to domains like business and economics. But they found that it actually applies to also many engineering disciplines, including to software programming. And what this rule basically says is that for many events, roughly 80% of the effects come from 80% of the causes. OK, so it's a rule in the sense of an observation. It's not like a law of physics, something that is embedded into the universe. But it is an observation that empirically you can see that in many cases, in many domains of human, we have this nice property that the cost or the inefficiencies are not quite distributed uniformly. Instead, they form these bottlenecks. And when we want to optimize something, we just need to detect the bottleneck. And if we solve that bottleneck, we can pretty much ignore everything else. And this should dramatically improve things. OK, so if we just focus on the 20% which are least efficient, we'll get roughly 80% gains. Of course, the numbers 80 and 20 are arbitrary. We're just trying to convey a more general sense here. And that's very important to remember when we optimize the software, because this rule is very, I mean, almost universally applies to software development. And the reason is when we look at software code, this will very often look at like something along these lines. So we'll have some preparations. For example, we'll take and parse the data. We'll do some processing. And we'll load everything to memory. Then we might have some big loop, which does some heavy computation. And then we'll have more data processing. We want to report the results, save it to files, and all of this stuff. Now, the nice thing about it is that sections 1 and 3 will be most of the code that you write. But in terms of CPU time, they will be quite negligible, and you won't have to worry about them. Whereas the second part will very often be a very small portion of the code, but that will be actually the part that is that makes most of the heavy lifting. And that's the part you will have to focus on when you try to optimize the code. And that's very good news for us. And that's actually what we can think of as Python's strategy to handle with inefficiency. So when I say that Python is really inefficient and it's very slow, it's actually not an accident. So it was actually a conscious decision of the people developing Python. They thought, and I think quite justifiably, that it's not very important to have an efficient language exactly because of this 80-20 rule. So they just wanted the language to be as nice and convenient to use as possible. And whenever you come across inefficiency, you just need to recognize this very small bottleneck. And then you can just, focusing on this very small bottleneck, you can use some native code. For example, you can use code that is written in another language. You can use a module that does the heavy lifting for you. And most of the time, you won't even have to write your own custom code using another programming language, because Python really give you ready-to-use many packages that will do pretty much every common operation that you can think of. So if you want to do something which is quite standard, like mathematical computations or regular expressions, then you have ready-to-use packages that will do it for you. And they are very efficient, because the crucial part with them, the crucial pathways within those packages are written in native code. So for example, in C. And they're just only wrapped in Python. So when you use a regex or when you use NumPy, which we're going to see now, then actually you do not need to worry about performance too much, because Python already gives you a library which is as efficient probably as a native code library. And that's really Python's strategy. Just instead of doing the heavy lifting yourself, just use a module that does it for you, only in the very bottleneck that you try to optimize. And in the rest of the code, you do not need to worry about it at all. And in very rare cases where you do not have a ready-to-use library, Python also makes it very easy to wrap code that is written in another language. So for example, you can use something which is called Cython, which we're not going to learn here, but it's not too complicated to take code in another language and to wrap it in Python. And Cython can also be used to even take a Python code and turn it into native code, which is more efficient. So it has some restrictions, but in principle, it could take some Python code, which is not efficient, and make it much more efficient. Just this one piece of code. So if you see that you have a bottleneck and you want something to be very, very optimized, you can also use Cython for that. But really, for 99% of the cases, and I think for all the examples we're going to encounter in this course, this really is not going to be a problem, because we're going to see that the already built-in libraries or the third-party libraries that we can use will really give us all the functionality that we need in a very efficient way. And the last thing that is important to keep in mind is this notion that what we call the speed of development is very often more important than the speed of execution. So when you write a piece of code, most of the time you should be more concerned about the time that it takes you to write this code than the time it takes your computer to execute it. And that, I think, is a very strong motivation to still use Python, which might be less efficient for the computer, but it's much more efficient for you, which is a more expensive and important resource to worry about. So that's really the motivation to use NumPy. Now, what NumPy is just a very efficient library and a very powerful one with very nice interface that allows us to do numerical calculations very, very efficiently. Okay, it's so fundamental. It's such a fundamental package that pretty much every package that you will install, any third-party package, will probably depend on NumPy anyway. So if you install some package, most chances it will install NumPy for you anyway, whether you want to use it directly or not. Now, the main things that will give you, which we're going to see, is what is called these powerful n-dimensional array objects, which I'm going to explain in a minute. And then you can make all of those nice computational algorithms on top of these arrays. So for example, it could be things like linear algebra and all kinds of maybe statistical or mathematical calculations, which you can do in these arrays. Now, if some of you have learned MATLAB and have some experience with it, you will probably feel very comfortable with NumPy, because it's really inspired by the way arrays work in MATLAB. So that was really the inspiration of NumPy. OK, so what are these arrays, which are referred to? So arrays are containers of data that are quite like lists, but different. And again, for those of you who are familiar maybe with older languages like C or Java, then it's much more similar to arrays in those languages than lists in Python. So I put here some key differences between Python lists to NumPy arrays that really explain the main differences between them. So the first thing is the size, which with Python lists, we saw its dynamics. So we can take a list and then we can extend it, or we can remove objects. So we can change the size of the list anytime we want. In NumPy arrays, it's actually constant in size. So like a tuple, maybe it's an immutable object. So you cannot change its type after you create it. A second key difference is that it limits the types of data types that you can use. So Python lists are just containers where you can put anything within it, and it doesn't matter. You can put a string, and then an integer, and then a Boolean, and then another list. So it just takes whatever you fit it into. Where in NumPy, it only accepts, in general, just one type. So if you want a NumPy array of integers, you'll only be able to put inside it integers. And if you wanted floats, then only floats, and so on and so forth. Now, NumPy array do support arrays of general objects, where in principle you can put anything within them. So it does work in theory, but if you do that, then you will probably lose most of the functionality the NumPy arrays give you. So the main motivation to use NumPy arrays is indeed in that case where you just have one type, and NumPy will, in fact, enforce it, as we're going to see. Now, Python lists are also just one-dimensional, so it's just a sequence of elements, which can be nested. So you can put a list within a list, and then you can think about it if you want, like a matrix or a table. But it's not really a matrix or a table. So it doesn't, for example, enforce all of the sublists within the bigger list to be of the same size. So it's just one-dimensional sequence of things which can be nested or not nested, but it's one-dimensional. Now, NumPy arrays, like in other languages, they can be multi-dimensional. So for example, if you take a two-dimensional NumPy array, you will get a matrix, where each element is described not by one index, but two indices. Now is the main motivation why we want to use NumPy arrays. So Python lists are quite slow, like anything in Python, whereas NumPy arrays are very fast because they're written in native code, and you can do calculations on them which are very fast in CPU and in memory, also very efficient. And the Python list won't give you pretty much any special functionality other than just putting in elements and taking them out. It's just a container of elements. Whereas NumPy arrays will give you a very rich arithmetic functionality, as we're going to see. So you can do really lots of calculations on them very efficiently and very conveniently. OK? OK. So let's see how it works. כן, בטח.
אז NumPy הרי יכולים להתחיל למשל טופול? כאילו, או שהם יכולים
So tuples and arrays are different things. Like I said, in principle,
אמרת שהם יכולים להכיל כאילו משהו אחד.
Yeah. Yeah, you can have a list of tuples. Now, in principle, you can have NumPy arrays which contain just objects. And then you could put anything within it, including tuples and strings and anything you want. But that's not the typical way in which you want to use the arrays, because it won't give you any special functionality. So you can have a NumPy array where each element is a tuple, but then you probably just shouldn't use arrays. You probably just prefer to use maybe just list or something. OK, so let's begin with importing NumPy. Now, the convention is to shorten the entire name of the module, NumPy, into just NP. It's really a convention you will see anywhere. So every time that you see Python code referring to NP, you can pretty much bet that this actually refers to NumPy, because everybody imports it this way. So it's very uncommon to see people actually just import NumPy. So let's begin with arrays. Like we've seen, we can create a list. For example, we can create a list with all the numbers between 0 and 19. And we can print it and see the type, and we see that this is a list. Now we can take this list and convert it into a NumPy array using the array function within the NumPy module, and then providing the list. This is not the preferred way to create arrays, because this goes through creating a Python list, which is inefficient. But you can do that if you have a Python list and you want to convert it into an array. You can use this conversion. and this will create an array. Now, if you print the array, it will look pretty similar to the list. You won't see that much of a difference, maybe a little bit different representation. So you can see that instead of commas, you have just spaces here. And you can see that the type is different. You can see that this is indeed an array. Now, more preferred ways to create arrays is to do it directly within NumPy without going through lists in the middle, which is less efficient. So most of the arrays that you want to create, you will have ready-to-use functions, which will do it for you. For example, you can use the arange function within the NumPy module, which is equivalent to the range function in Python. It will create you an array of some range. You can use the zeros or ones function to create an array, which is just a constant 0 or a constant 1. Or you can even create an empty array of a given size. Say I want an empty array with 30 elements. And you can see that it's not really empty. It does contain some pretty random numbers. And the reason is that the empty is supposed to be more efficient. So when you create an empty, it just allocates a chunk in the memory that should contain the content of the array. But it doesn't actually erase what was previously in this chunk of memory. So whatever garbage is in this unallocated memory, it will just be there, waiting for you to override it when you put some content in your array. So using the empty is slightly more efficient because it doesn't need to initialize the value. It just allocates a chunk of memory and gives you whatever garbage is already there. But the downside is that it could be a little bit dangerous because then you'll get some pretty random content. And if you then not override the empty or you have a bug, you might end up in a situation where each time you execute it, you might get something a bit different because it contains a random component within it. It's not completely deterministic. OK, so these are four quite common ways to create arrays.
When I run it, I get 30 zeros. I don't know if I'm the only one.
Yeah. The empty one?
Yeah.
No, so it's just, I guess, an accident that in your chunk of memory it happens to be all zeros, but it's not guaranteed in any way.
Just randomly assign 30 zeros?
It's not a random, OK? It's not a random in the sense that it actually generates random numbers. It just takes a chunk of memory, which is unallocated at the moment, and just gives you whatever there is there. So if you had an image of a cat in this chunk of memory, it will give you whatever was in the pixels of the cat. And that's the kind of garbage you're going to get. So I don't know what garbage was in your computer, but maybe it had a lot of zeros. So it's not really random, but it's arbitrary.
Why is it better as zeros or, for example, none or something?
Yeah, so if you anyway are then going to override it, and you are going to maybe create a loop and then to assign your own values, then it is slightly more efficient because it doesn't need to go to the trouble of erasing or putting any other specific value in the memory. It just allocates the memory, and that's it. And you're left to do whatever you want with it.
But if I would put zeros, I would not allocate the memory?
You mean the zeros function?
Yeah.
So the zeros allocates the memory and then also initializes everything to zeros. So it does this extra step of actually overriding the values. Now, anyway, it all happens much more efficiently than in Python code. So it all happens using native code, which is much more efficient than Python. So creating an array of 10 zeros is much more efficient than creating a list with 10 zeros, OK? Because an array is much more efficient than a Python list, OK? Now, these arrays look and work pretty much like list works. So if you want to do assignment or slicing, it works pretty much the same way. So we can, for example, create an array of size 20. And then we want to take the element in index 5, so the 6th element, and we override it with 77. And you can see that it was indeed overridden. And we can also do slicing just like with lists. So we can take everything between position 3 to 10, not including 10, with jumps of 2. And we'll get the appropriate subarray. Now, crucial difference is that the arrays, like I said, they have a type. And you can access it using the dtype attribute of the array. Okay, so you can ask what is the data type. So for example, the array I created here is an array of integers. And when I print the data type, you can see that it's an integer of 32 bits. So you can see that this is indeed an integer. And if I try to assign something which is not an integer, for example, if I want to take the 6th element and assign 0.2 to it, then it will be converted to an integer, whether I want it or not. It will be converted to 0. Now, if I want to create a range of 20 elements of type float, which I can put 0.2 within it, there are several ways I can do it. Some are more recommended than others. The first way to do it, which is the least recommended, is to go back to the array constructor of NumPy and to give it some Pythonic object that I want to convert into an array, and then to explicitly state the type. In this case, I want it to be float64. And this will take this range and convert it into an array of this type. And then I can put the value that I want. And you can see that it's indeed 0.2, like I wanted. But this is very not recommended because, again, this goes through creating a Python object, which is far less efficient. I want to keep everything as far as I can within the context of NumPy without resorting to Python operations, and it will be much more efficient. So another way to do that is to use the arange, like we saw before. This will create an integer array. And then I can use the asType function, which converts an array to a different type and providing the type that I want. OK, so this will create an array of integers. And then it will turn it into another array of floats, which I can then work. This is much more efficient than the first option, but it's not the most efficient way to do that either. And the reason is because here we create two different arrays. So like I said, the arrays are immutable, so you cannot really change them. So any operation that you do to arrays, it will actually create a new array. So the asType will not change the original array. It will create a new array of the type that I want. And so this operation will actually create two arrays. So first an integer array, and then a float array. And that's the reason that the most recommended way to do that is just to specify that I want floats right at the beginning. So right when I call the arange function, I can give the dtype as a keyword argument to this function and specify that I want it to be of type float. And now I will get a range of floats right at the beginning, creating just one array. OK? Now here I specified exactly that I wanted it to be a float 64. But I don't have to go into too much specifics. So I can just give something general, like an int or a float, and just leave it to NumPy to worry about the specifics. So here, NumPy will know if I want a float, it will know to choose float 64 is the specific type. And for most environments, float 64 is really the standard type. So for example, if you create an array of zeros or most constructors of array, that will give you float 64 as the default data type. OK, so we've seen one-dimensional arrays. But like I said in the introduction, we can have multi-dimensional arrays. And we can actually give few dimensions by simply using a tuple when we specify the size. For example, in the zeros function, which creates an array of zeros. So if I give a tuple with 5 and 3, it will know that I want a two-dimensional array with a first dimension of size 5 and a second dimension of size 3. So this will essentially create a matrix with 5 rows and 3 columns, all with zeros. And if I use the shape attribute, I will get a shape of this created array, and you can see that it's 5 and 3. the shape that I gave it. It's important to note that if I use the len function on arrays, it will not give me the size of the entire array, just the first dimension of the array. Okay, so the length of z is considered to be 5, because that's the number of rows. That's the size of the first dimension of the array. If I want the overall size of basically the product of all the dimensions, I can use the size attribute, and then I get 15 as an answer. So 5 times 3. I can use the reshape function, which, yeah.
אם אתה רוצה את האורך השני, if you want the other like length, like you have like.
Yeah, good question. So if I want in a different dimension, I can use the shape, which gives me as a tuple, and then I can just access it in the dimension that I want. So if I go to dimension number 1, that's the second dimension, I'll get the number of columns. Yeah. So we've seen that we can use the as-type function to convert a given array into a different array of a different type. And similarly, we can use the reshape function to convert an array to another array of a different shape. So for example, instead of 5 rows and 3 columns, we want 3 rows and 5 columns. So we can use the reshape function to change the size of this array. Or we can just give one number, and then we'll reshape it into a one-dimensional array of size 15. One moment. But it's important to make sure that the new shape that you give it really matches the current shape. So in essence, it has to be the same size. So if it's an array of size 15 overall, then the product of the dimensions needs to sum up to 20. So if I try to convert it into 4 and 5, which is of size 20, it will say that it cannot reshape an array of size 15 into shape 4 and 5. Okay, and this can go for as many dimensions as I want. So I can use the A range to create to create the range of all the numbers between 1 to 2 times 3 times 4 times 5, which I think is 120. And I can then reshape it into a 4-dimensional array of sizes 2, 3, 4, and 5. Okay, and you can see that what I get is a 4-dimensional array. Now the screen is only 2-dimensional, so it's a little tricky to visualize that, but you can really see that I have 2 main blocks here, which correspond to the first dimension of size 2. And then each of these blocks is subdivided into 3 smaller blocks, which you can see here, where each of those is a matrix with 4 rows and 5 columns, which what you see here. There was a question earlier?
When you do a reshape, does it keep the order?
Yeah. So yeah, it's a little tricky to define exactly what kind of ordering is preserved when you do a reshape. But yeah, there is a logic to it. So you can see that everything here keeps the ordering. So you see that I took the numbers between 0 to 119, and you can see that it's indeed sorted in this way when I print it in the new shape.